Okay, so I would like to share with you an example of how actually we can use density to calculate mass or volume. In the first example here, for example, given hexane, okay, having a mass flow rate of 6.59 gram per second, and the density given is 0.659 gram per centimeter cube. So what you can do is actually you can calculate the volumetric flow rate given the mass flow rate of hexane divided by the density, which is 6.59 divided by 0.659, and you will get 10 centimeter cube per second. Okay. Another example is you are given volume of a chemical component CCl4, and you actually the volumetric flow rate is 100 centimeter cube per minute, and the density is given as 1.595 gram per centimeter cube. So here you can calculate the mass flow rate, which is 100 multiplied with 1.595, and you will get 159.5 gram per minute. Another example that we can actually use is to convert the mass flow rate to volumetric flow rate or vice versa. Okay, so we have learned in the unit and dimension where we use this particular table, so it would assist you in order for you to convert the units. Here, for example, like you have the volumetric and mass flow rate. Calculate the volumetric and mass flow rate if a volume of 500 liters of water is collected for a period of 5 minutes. So you know that you collect 500 liters of water and the period of 5 minutes. So simply you can calculate the volumetric flow rate is 500 divided by 5. Then you'll be able to get 100 liters per minute. And given the density of water is 1000 kilogram per meter cube. So here, when you construct the table is that you put 100 liter per 1 minute in 1 minute, and then you know that 1000 liter is equivalent to 1 meter cube. Okay, and you know that 1 meter cube and 1000 kilogram per 1 meter cube is actually the density. So here you can calculate, and when you multiply everything, you cancel out liter with liter, meter cube with meter cube. 100 multiplied with 1000 divided by 1000. So you cancel out, you'll be able to get 100 kilogram per minute. So this is the mass flow rate for this particular process. So let's talk about molecular weight. Molecular weight is actually the sum of atomic weights. So for example, like if you have CO2, so each of these atom has its own molecular weight, and you have to sum everything, which you have learned this in your chemistry subjects. Okay, so the basis here is the atomic weight of 12 carbon. So the exactly amount is actually the exact molecular weight is 12, but for a naturally occurring carbon is 12.01115. Okay, and here this is where actually from that particular basis, this is where actually we'll be able to calculate all other atomic molecular weight. For example, like for oxygen, we have O as 16, but oxygen is actually 32. Okay, and we have for example, like we want to calculate CO2 is actually 44. Okay, because 32 plus 12, then you got 44. And you always know that 1 mole is equals to 6.023 times 10 to the power of 23 molecules, which is we learn in chemistry as Avogadro's number. So these are all important information that you need to know as the example of the process variables. Another thing that we have to know is actually between mole fraction as well as mass fraction. So mole fraction is actually always denoted sometimes with yi or xi. Okay, y usually represent the component in the gas form, and x is the component in the liquid form, where actually you can calculate the mole fraction of certain component in a liquid. Then we usually use x. If let's say we calculate the one in the gas component, we use y. But here we are sharing with you, if let's say you want to calculate a mole fraction for a species, it's actually the number of mole for that particular species divided by the total number of moles that is actually that we have in that particular system. For example, if let's say you have a container, okay, a container that contain oxygen as well as nitrogen, and you want to determine the number mole of a species of oxygen only. So you can calculate the mole fraction for oxygen is the number of moles of oxygen in that particular container divided by the total number of moles, which you have to add up the total number of moles of oxygen plus with the nitrogen. Okay, so that will give you the mole fraction. However, in order for you to calculate the mass fraction, it is actually of a species. So for example, like you want to calculate the mass of an oxygen in a container which also contain mass of it also contain nitrogen. So you have total up the mass of oxygen plus mass of nitrogen here, okay, and you take the mass of oxygen divided by that numbers, then this will give you the mass fraction, which is also we call it as weight fraction. Okay, so for example here, if you want to determine the mole fraction, okay, the mole fraction yi here, for example, this is nitrogen, so you have number of moles as 40, and then here you have oxygen 30, CO2 10, and you have a total number of 80s. So in order for you to calculate the mole fraction is simply 40 divided by 80, then you get 0.5. And CO2 is 10 divided by 80, then you got 0.125. Just to make sure that if your calculation is correct or not, total up everything, then you should get equivalent to 1. If you do not get equals to 1, perhaps there may be some miscalculation that you have done. As such, you can also determine the average molecular weight. Okay, so for example, like you already determined that mole fraction as follows, which is 0.5, 0.375, and 0.125 for different kind of components. And you know that the molecular weight for each of these components, for example, nitrogen is given at 28, 32, and 44. You want to determine what would be the molecular weight, average molecular weight. So what you can do is actually use this particular formula where each of the mole fraction is multiplied with the molecular weight.